Hello students, today we are going to see our first experiment of radiation and microwave technique. That is to plot the radiation pattern and to calculate the performance parameters of simple dipole and folded dipole. Basically, the radiation pattern is nothing but the radiated power at different location in the angular space. Angular space means what exactly? For example, suppose this is your z-axis, this is your y-axis and this is the x-axis. Then E field components are suppose in the z-axis, then always H field components are perpendicular to E field. Therefore, it will be in the y-axis and wave propagates in the x-axis. Therefore, when we are going to measure the radiated power, we have to consider the both azimuthal plane as well as elevation plane. Azimuthal plane means xy plane and elevation plane may be xz plane or zy plane. And angular displacement for azimuthal plane is always 0 to 360 degree, and for the elevation plane angular displacement is 0 to 180 degree. Therefore, from the radiated power by the antenna, we can plot the radiation pattern. Then this is always the main lobe, which is called as the main lobe. It means the maximum radiation in some particular direction. That direction may be anything depending on the antenna structure. It may be 0 degree, it may be 30 degree, it may be 90 degree. Then these two are called as the side lobe. The lobe which are adjacent to the main lobe are called as a side lobe. And then remaining there may be n number of lobes. This lobe which is exactly at the back side of the main lobe is called as the back lobe. Then from the main lobe we can calculate the half power beam width. Half power beam width is nothing but the angular displacement or angular spacing between 2 points where the radiated power is half of the maximum power. Then this point is called as the null. Null means the radiated power is 0, and these two nulls are called as a first null. The spacing between these two null is nothing but the first null beam width. Then from this radiation pattern we can calculate the different performance parameters of the antenna. First parameter will be maximum bore side. Maximum bore side means the direction at which the maximum power is radiated by the antenna. Then just we have seen how to measure the half power beam width. Then from the radiation pattern we can calculate the gain of the antenna. Gain of the antenna is nothing but the maximum radiation intensity of test antenna. In our case, test antenna is either simple dipole or folded dipole. Maximum radiation intensity of test antenna divided by maximum radiation intensity of reference antenna. Generally, we consider the reference antenna is isotropic antenna because isotropic antenna is an ideal antenna which radiates equally in azimuthal plane as well as in the elevation plane. Therefore, generally reference antenna is always considered as an isotropic antenna. Then we can calculate the return loss using this equation, which is nothing but the minus 20 log of gamma, where gamma is nothing but the reflection coefficient. Then from this reflection coefficient we can measure VSWR. VSWR means voltage standing wave ratio. In our theory session already we have seen what is meant by standing wave. Standing wave is nothing but the combination of incident wave plus reflected wave. And generally standing waves are undesirable parameter. Therefore we can calculate the voltage standing wave ratio from the reflection coefficient. 1 plus gamma divided by 1 minus gamma is nothing but the VSWR. Then from VSWR we can measure impedance of the antenna, ZL. S is nothing but the VSWR. S equal to ZL divided by Z0, and this Z0 is a characteristic impedance of the cable, which is standard impedance 75 ohms. Then we can measure the front to back ratio also. Front to back ratio means the maximum radiated power in some direction divided by radiated power by the antenna exactly in the opposite direction. Then we'll see actual setup and actual performance parameter, how to calculate using this our test bench setup. Now we are going to see how to perform this experiment. First of all, I will tell you the different types of antennas. This is nothing but the simple dipole antenna. Then this antenna is called as a folded dipole antenna. Here you can clearly see this antenna is folded here, and because of this folded dipole antenna, the radiation impedance of the antenna is 4 times greater than this simple dipole antenna. Here the excitation signal is applied using this BNC connector to this antenna. Then there are some different types of antennas also. This is called as a microstrip antenna. In microstrip antenna, this is a microstrip patch, circular type microstrip patch, and this backside is called as a ground plane. In between patch and ground plane, this material is nothing but the dielectric material, which is called as a substrate of the antenna. Then this line is called as the feed line for the antenna. With the help of again BNC connector, we can apply the excitation signal to this antenna. Then there is one more different microstrip antenna, which is nothing but the rectangular microstrip antenna. Here you can observe this antenna is rectangular microstrip patch, and again backside is ground plane, and here the inside field excitation technique is used to apply the excitation signal. Then there is one more type of antenna, which is called as a slot antenna. You can clearly observe that this is nothing but the slot antenna, and this slot is nothing but dielectric material surrounded by the conducting material. Here you can give the excitation signal to this antenna. Then there are some array antennas also. This you might have seen this antenna. This is nothing but Yagi-Uda antenna, Yagi-Uda array antenna. Here this element is called as the feed element, and this is nothing but the reflector, and these elements are nothing but the director. Actually, if the antenna is kept like this, then maximum radiation would be in this direction. Reflector reflects the electromagnetic energy in this direction, and directors are used to direct the electromagnetic in this direction. Therefore, we can use this Yagi-Uda antenna to improve the directive gain of the antenna. Then this is another type of array, which is called as the log periodic antenna. In this log periodic antenna, we can observe here different antenna elements. Only difference in the Yagi-Uda antenna and log periodic antenna is that we have to apply the excitation signal to each antenna element. You can here observe that this excitation signal is given to each antenna element, whereas in Yagi-Uda antenna the excitation signal is given to only one element. Now we are going to see how to calculate the different antenna parameters for simple dipole antenna. Here you can see this is a transmitter to transmit the electromagnetic energy. This transmitter is connected to this antenna, and here I have set the frequency of the transmission is 700 megahertz. Why 700 megahertz? Because our all antennas are designed for the 700 megahertz. Therefore, for the transmitter, the frequency should be 700 megahertz, as well as at the receiver, the frequency is also 700 megahertz. And this antenna is common antenna, which will act as a receiving antenna, and this our test antenna will act as a transmitting antenna. Here you can rotate the position of the antenna from 0 degree to 360 degree, and you can take the readings for each angle. You can vary the antenna position like from 0, then 10, 20 like this, and you can measure the received power at the receiver. Now at this moment the position of